Momentum of system of particles. So still we consider the same situation. We have a system of particles. It means many of particles, and for further subsequent deriving of equation we can select one point, representative point from the system. So there is an external force acting to one point mi with mass mi, and there is also, or can be, the reaction force from other points, let's say from point j or particle j to our point I. Okay, so the total momentum of the system, total momentum of the system is given by sum of all momentums of particles. So total momentum P is given by sum of momentum of all points present in the system. So this is that. Okay, and equation of motion of one particle, our ith particle, so it means ith particle is derivative of its momentum. It is this with respect to time, and it must be equal sum of forces acting to that particle. So at first it is an external force, a resulting force acting to ith particle, and also it is a sum of internal forces acting from other particles over J. Okay, so this is an equation of motion of one selected particle, and we can write as many equations as many particles we have. So if we have n particles in the system, we can write n such like equations. Okay, and after that we can sum them. We can sum all of these individual equations. So by summation of all equations from 1 to n, we get so it is ith equation. We get d over dt of sum mi vi over I is equal sum of external forces plus sum over I of summations of all internal forces over J. So we derived earlier that this is equal 0 because sum of all internal forces is equal to 0 because all internal forces are subjected to the law of action and reaction, and every action compensates in this summation every reaction. We made some small trick here, if you noticed, so that if we make sum of left sides of equations, so we normally get sum of d over dt, I mean this dmi vi, okay, so over I have written this, okay. If we make a sum, first we make a sum of derivatives, and look, here it is opposite, so we assume that sum of derivatives is equal to derivative of sums. Okay, like this, so we can swap it. Okay, so it's only a note for this, for better understanding why it is written in this way, in opposite way. Okay, so we assume the applicability of this. So this is a sum of total momentum as we write it here. Okay, so it is dp over dt. It is this left side of equation because sum of mi and vi is p, so it is a total momentum of all the system. Okay, so derivative of momentum of entire system of particles with respect to time is equal sum of all external forces acting to individual particles. So sum of all external forces is a total resulting force. Okay, so this is the final law, that the momentum of system of particles change in time under action of external force only. So it is written here, change of momentum of system of particles in time is equal to resulting external force. This is a change of momentum in time. And second remark, internal forces don't influence total momentum of the system. So this doesn't appear here. So we can in fact formulate a law of change of momentum of system of particles, which is here. This is this formulation in differential form, and we can also formulate it in integral form. So this is in differential form, and here it will be in integral form. Okay, so when we integrate this equation, so we get that P2 minus P1 is equal integral of Fe, so it's total resulting force from T1 to time 2 with respect to time. Okay, so this is an alternative integral formulation of this law, and both formulations we can rewrite to component equations. So this is an example of component equations or equation. Okay, so if we need to rewrite it in component equations or equation, we can do it like this. So this is a sum of mi vi as a component x, for example, at state 2 over I minus sum of mi vi x at state 1 over I is equal integral of external force in time between time 1 and time 2. So this is an example of how to rewrite this vector equation into component equation. And finally, we can continue with formulation of law of conservation of the momentum. So if we have a law of change, so it means P2 minus P1 is equal to this. So when P1 is equal to P2, so when P2 minus P1 is equal to 0, so under the condition that the right side of equation I shown you before is equal to 0, so it means that this integral must be equal to 0. So it is impulse of external force or forces. Yeah. So then we can write that sum of mi vi x2 minus, or let's say is equal mi vi x1, and it is constant. Yeah, so it is a law of conservation of momentum of the system. So the momentum keeps constant over the time. We can accompany this theory by short example. Ideally plastic collision. What it is? Ideally plastic collision. So let's assume that we have some trajectory and there is a particle with mass m1 and velocity v1. So there is a velocity v1 and there is another particle m2 with velocity v2 equals 0. Okay, so it's at a rest. And let's assume that material of both particles is ideally plastic. What does it mean? That after collision there is no resilience. So it means if you drop this body from the ideally plastic material to the ground, it doesn't jump back. Okay, there is no energy resilience, or energy is absorbed to deformation of this body. So it's like plastic material. So what happened now? This is given, okay, or we can write it here. So given there is mass 1, mass 2, v1, v2, and what is a final task? It is to calculate the velocity of the system after collision. So v star, okay, is, so it's a velocity after collision. So this is a state before collision. And after collision. So what happened? This is at the rest and this particle is heading to this position. So the collision happened. So there is something like collision. And because both materials are ideally plastic, they totally mixed together and they continue as a one big particle with mass m1 plus m2, totally mixed together with unknown velocity v star. So this is a velocity of the system after collision, and we are supposed to find this final velocity. So we use a law of conservation of momentum of system of particles. Why we use a law of conservation and why we don't use a law of change? Because for change of total momentum of the system we need acting external force. There is no any external force. There are only internal forces, action and reaction. Okay, so there is no external force, so we use this. Yeah, this is applied in this example, so we use this law of conservation. Okay, so we can write the equation. On the left side there is a initial state, so there was a this is on the left side there is a total momentum of the system before collision, so m1 v1 plus m2 v2, but v2 is equal to 0, so this multiplication is equal to 0, and it is equal to the state after collision. So before, after. Okay, here it is opposite, it doesn't matter. Before and after. After collision we have system of the same mass with unified velocity v star. So we can derive a v star very easy from this. So it is m1 over m1 plus m2 by v1, and this is resulting force of the system after collision. Sorry. Okay, so once again, I'm sorry. So this is state before collision. This is sum of momentum of first particle with momentum of second particle. This is 0. The second particle has no momentum because it doesn't move. Okay, so the momentum of second particle is 0, and this sum before collision is equal to the momentum of the system after collision, and both particles are mixed or matched together, so the mass of the system doesn't change. It's m1 plus m2, and both particles continue with the same velocity. Okay, and from this we can very easy subtract this. Okay, or not subtract, but express this. Yeah. So this is a final result.